Hello, everybody. Nice to see you all. And I just want to first make sure, does the sound work? I hope it works. Okay. Well, first of all, I'm Po-Shen, and I would like to welcome everybody to our Math Kangaroo live song. Actually, it's a great pleasure to collaborate with Math Kangaroo because their questions are really, really creative and novel. And actually, the Math Kangaroo competition just happened. But I want to let you know, we're being very careful here. We're only going to talk about past problems, not the ones from this year. The official collaboration where we talk about the problems from this year will be later after it's legal to talk about them. But I'm not actually going to be the one that's leading this live stream because as you can see, I'm in a random parking lot. I'm in Newark, New Jersey because I just finished giving 3 talks this weekend, one in Philadelphia, one in New Jersey, and one in Great Neck, Long Island. And I'm flying back tonight. But you're in really good hands because you have Aiden and Sneha. And I'll pass it off to them and they'll introduce each other because I've worked with both of them. They're awesome.
Awesome. Okay. I will first introduce Sneha then. So Sneha is really good at math competitions. First of all, she participates in a lot, such as math counts and RMAL. And she's actually represented Minnesota twice at Math Counts Nationals, and she placed top 56 once. So apart from math, she also enjoys various science extracurriculars and playing the cello.
Yeah, and my co-teacher today is Aiden. And like me, Aiden also participates in many math competitions. And besides from math, he is also the captain of his science boat team. And besides academic activities, he also hangs out with his band and his basketball team. So who's excited to do some math today? Aiden, why don't you start us off?
Awesome. Okay, let's do this. So, first question, basically what we're gonna do is we're just gonna go through a select amount of questions from the 2019 Math Kangaroo grades 7 and 8, and we'll sort of just have a discussion, talk about it, and hopefully we can get through everything, and as long as we have a great time, that'll be awesome. So, we start with question 1. Um, in this question, it asks which cloud contains 4 even numbers. So this might be a little bit hard to see. Let me see if I can blow it up a little. Okay, here we go. So 4 even numbers. I think this is a pretty straightforward question. So A, it's wrong because there's a 3. Um, B, it's wrong because there's a 33. C, it's wrong because there's a 3. D is wrong because there's a 1. So that remains the answer choice should be E because it has 10 to 34, 58. Okay, starting off nice and easy. Answer choice is E. Awesome. Okay.
All right, so now let's move on to this question, which deals with this 3 by 3 cube, which is built from 1 by 1 by 1 cubes. So we see that some cubes are removed from front to back, from left to right, and from top to bottom as shown. So how many 1 by 1 by 1 cubes are left? Well, let's see how many there were before we had any removals. So to begin, we have 3 times 3 times 3 equals 27 cubes. And then we remove some amount of that. So who can tell us how many that we removed? I see a lot of answers of C in the chat, but not a lot of explanation. So let's try to get some explanations going too. Okay, so I see a lot of remove 6 or remove 7. So we have some disagreement on whether we remove 6 or 7. Well, something I like to do in this problem is consider it layer by layer. So the very top layer, if we consider it from a bird's eye perspective, it's going to be basically this square and divide it up. And we have the portion of the outside shaded in. and we kind of have the center cube missing. So that eliminates one cube from the top. But how many cubes do we remove from the other layers? Well, yeah, you guys are right. We have to remove the core too. That's a great idea. So when we consider the middle layer is not going to look so much like this. If we take a cross section and we see the middle layer, we'll only have the 4 cubes on each corner. And that means that we removed 5 more cubes just from this middle layer. And actually, this cube is really interesting because it's symmetric on all sides, which means that the bottom layer is identical to the top layer. And we also have 1 cube removed there. So if we add this all up, we get 1 plus 5 plus 1, which is 7 cubes, and we get 20 cubes, or C as our answer. And let's check that, and we should get 20. Great job, everyone.
Awesome. Yeah, I really, really liked all the explanations we started to see down here in the chat. Those are great. Keep those up. And let's move on. Question 5. So we're going by odd numbers, it looks like 1, 3, and 5. Which of the diagrams below cannot be drawn without lifting your pencil off the page or drawing along the same line twice? So this one's actually quite fun. I'm gonna say there is a way, I think, like graph theoretically, we can talk about that in a moment, but if I did this problem, I would just try to trace each one, and that'd be kind of fun. So we can't lift our pencil and we can't draw along the same line twice. Obviously, B is we can do it, so that's not our answer. You just draw the sort of thing. I wish I could like do this in real time, but okay, no B. Let's try A. So yeah, the thing here is that you can't draw along the same line twice, but you can draw along the same point twice. So the strategy for A that we can use here is to just draw the square first, and then we can draw the circle, because that doesn't retrace any lines, and we don't lift our pencil off the page. So here we go. There's the square first, and we can just draw the circle. Yep, square and then a circle. That just touches a few points. For C, we can split it. We can think about it in 2 ways. 2 triangles stacked on top of each other. So we can actually just do the first triangle and then do the second triangle. And yeah, I'm gonna go here, and then I'm gonna go here, and I'm gonna go here, here, and here. So that one's possible. D. Yes, okay. I was thinking for a moment. I think I'm gonna use the same strategy here, basically. Just use the triangles again. And maybe we can do it. Let's see. So I'll start from the middle. That seems like a good place to start. I'll complete this triangle. Actually, this one might not be possible. I don't think this one's possible because I just keep getting stuck on an end if I keep doing it. But let's check E. E, I'm gonna do the sort of triangle method again. And we can start from the top, do this triangle here, do that, do that, do that, do that. So it looks like our answer is D. But is there a systematic reason why? It's actually a little bit hard to think of if you've never seen this before, but if we look at the figure for D again, so if we cannot lift our pencil off the page, that means it basically has to go through one straight line. And if we can't do the same line twice, that's the same thing going through a straight line. So let's see. I feel like I want to see if we can prove that this one is not possible. But hmm. Oh, I think the way you can do this is that there's like this graph theory thing, right? It's like you have to visit a point, right? And if the point has an odd number of times, you can't revisit it. So in like a sort of like graphical sense, we have to start from a point with 3 lines coming from it and end at a point, or an odd number of lines coming and end at a point with an odd number of lines. So this one has 4 odd number lines, right? So we have to start and end at 4 points, which is impossible. So that's the graph theoretical explanation, but in all honesty, I think drawing was good enough for this question. And the answer is indeed D. Okay.
All right, that was a fun graph theory problem. Let's look at our next problem. So we have some combinatorics here, I guess. So in a race, Lothar finished before Manfred, Victor finished after John, and Manfred finished before John, and Eddie finished before Victor. Who finished last of these 5 runners? Okay, so what I like to do is I kind of like to draw like a number line. So on the number line, if it's more towards the right of the number line, it's going to be finishing first. So Lothar finished before Manfred. So we're going to have an L somewhere here and an M somewhere here. We know Victor finished after John. So if Victor finished after John, we're going to have a J and then a V, something like that. And notice that the J and the V, right now we don't have any correlation between this pair and the L and the M pair. But we do know that Manfred actually finished before Jean. So that means this pair would actually go over here. So we'd have J and then V. And finally, Eddie finished before Victor. So if Eddie finished before Victor, he could theoretically be anywhere here. So who finished last of these 5 runners? Well, it says, I see in the comments that Victor is the only one that has after. So Eddie finished before Victor. That's an interesting approach. So, I see another solution, chat. L is less than M is less than J is less than V, and E is less than V. So who finished last of these 5 runners? It seems there's some disagreement in the chat. So let's try to put a scenario together and see if it works. So let's say Eddie finished before Victor. We don't have a lot of information on Eddie, which makes me consider where we should put Eddie. How about we put Eddie somewhere here? So, Eddie finished before Victor. Sorry, actually, Eddie is on the other side of this number line. We have this. So who finished last? So now all we have to do is read off the number line and see that Lothar is the last of the runners. Aiden, any thoughts on this problem?
I think the number line method is the best way and the best way to organize this problem. For a lot of the earlier questions, I actually realized some can actually get a little bit challenging near like the 7 through 15 range. But a lot of those challenges can be resolved if we just organize our work properly. So seeking the best way to organize our work is really important for some of these, especially early on problems. So yeah, I really like the number line approach.
Okay, let's see if this is right. So I might have gotten some of these mixed up, so feel free to correct me if I'm wrong. Let's see. We indeed get, it is Victor. So let's go back and check our organized work. So Lothar finished before Manfred. So I think I might mess myself up with this, but this would be the fastest. So if it's further right, you would finish first. So Lothar finished before Manfred. Victor finished after Jean, and Eddie finished before Victor. Aiden, do you spot an error with this number line? Let's see if we can work through this together.
So I think the thing, okay, so we have this information about Victor, which is that Victor finished after Jan. So that's one thing. And we want to find the last of these 5 runners. Another thing we know about Victor is that Eddie finished before Victor. So that is probably an important point as well. So if we're doing something like before, right? This is finishing before and this is finishing after. So the after side should be the last side. So we're looking for who's on the very right over here. We know that Victor finished after Jan and Eddie finished before Victor. So this is a little bit confusing because when you like swap the things, right? It's like you can say Victor finished after Jan, and you can also say Jan finished before Victor. So I think we just have to be really careful there. In this case, if Lodar finished before, uh, yeah, these names are Manfred. Okay, Victor finished after Jan. Manfred finished before Jan, so I think it looks something like this. And then Eddie finished before Victor, so Eddie is somewhere in here. So that just makes Victor the last one. Yeah, I think the main confusion might come from the before and afters, right? And the orders of the names. That's a little bit confusing. Yeah, does this look good now?
Yeah, I think I put Eddie at the end because I wasn't so sure where Eddie is going to be placed. But I guess it's important to note that it doesn't really matter where Eddie goes in this number line. It just matters about the placement of the other four.
Yeah, awesome. Okay, let's move on. Question 9. Okay, another geometry question. I feel like every time it's like a cycle of like some non-geometry question and then a geometry question, but it's pretty fun. Anyways, large square divided into smaller squares, fraction. What fraction of the large square is colored gray? So, um, what's the general approach for this, do you guys think? Like, there's a general approach usually for these types of questions. Okay, so divide the large into the smallest first, counting squares, split the other squares into equal parts, as the top left corner to make it easier. Yeah, there's a lot of different ways. I think I can talk about two of the most common ways. One is, as someone mentioned, to split the other squares into equal parts, because that way we can get like a common denominator and then we can find the numerator. So this square right here has 9, right? We can technically split each of these other squares to get 9 as well. I'll do it for this square. Oh, that's a highlighter. Okay. We can split this one into 9s as well. Yeah. So each one we can split into 9s, and then we're going to get equal parts, which is going to be 4 times 9 as the total, which is all of each of these squares. And if we want the numerator, we simply have to add all the gray squares. So we have 7 here, and down here, even though I didn't split it here, this one would be 3 times 3 for 9 of these small squares. So 7 plus 9, we do that. That's 16 over 36, which is equal to 4 over 9. So that's one really great way to get the answer already. But I also saw some people mentioning another way, which is to just kind of directly use fractions, right? Obviously, this gray square down here is 1/4 of the entire big square. So this part represents 1/4. This thing is a little bit more complicated, but the strategy we can use here is we know that this square takes up 1/4 of the entire big square, and we can actually multiply that now by 7/9, which is how much the gray squares take up out of this square. So in a sense, we're basically just going from small to big, right? We start with 7/9, and then we multiply by 1/4 because we got a whole nother three empty squares here. So we can do 1/4 plus 1/4 times 7/9. That's going to get us the same answer of 4 over 9. Okay, that will be answer choice D. Let's see. That is correct. Okay.
Okay, now we have another non-geometry problem actually. So it reads, a different 4-digit number was written on each of 3 pieces of paper. The pieces of paper are arranged so that 3 of the digits are covered, as shown. The sum of the 3 4-digit numbers is 10126. What are the covered digits? This is a fun problem. So actually, it's helpful that we already have one of the numbers. So we know that we have 1243 and then 2, 1, blank 7. So the blank kind of represents numbers that we don't know. And finally, we have blank, blank, 2, 6. So we want to find which are the covered digits. Interesting. So let's see if we can add it up and do some deduction. So over here, we have that the last digit is 3 plus 7 plus 6, which is 6. And that's good because it matches up. I don't know what we would have done if it didn't match up. But then we have something that carries over. So it looks like you can't quite see that part. So we have 6, and then we have 4 plus 2 plus the extra 1 that we get from carrying over. So we have 7 plus this mystery digit that equals 2. So that mystery digit must be 5. So we get 2, 1, 5, 7. So just to double check, we have 16 and then 9, 11, 12. Nice. Now we need to make sure that we satisfy 101. So now we have to look to the next digit, which must be 1. So let's see if we're doing any carrying over again. 4 plus 5 plus 2 plus 1 is equal to 12. So we have to carry over another 1. So we get 2 plus 1 plus 1 is 4. And to make 1, we have to add 7 to that. So we're not really making 1, we're really making 11. So we're making another 1. And then finally, we did some carrying over, and we got another plus 1. And now we have to make 10, which are the first 2 digits of our number. So we have 1 plus 2 plus 1, which is 4. We add 6, and we should get 10. So now back to the original problem. We have, what are the digits that we added? So we have the 5, we have the 6, we have the 7. So going back to answer choices, that is option choice A, as many of you were stating in the chat earlier. And let's just check that. Yay, we got A, 5, 6, and 7.
Okay, let's see if the next one is a geometry problem. Okay, it is basically a geometry problem. So, question 13. This time we have another grid problem, a bunch of gray squares and a bunch of not gray squares. The question is, which of the following 4x4 tiles cannot be formed by combining the two given pieces? So, one thing I think we can all agree on is that the sort of general configuration is we're gonna like plop this square into here, and then maybe we can turn the two things, right? Like maybe this could become an upside down. Like the obvious configuration is kind of like this, right? But we could also have something like this. And we can also turn this square on the inside to like rotate it and get stuff. So I'm first gonna do the easy thing. I'm gonna count how many gray squares there are, because we know that putting them together, no matter how we put them, there's gonna be the same number of gray squares. So there's 3 gray squares here and 3 gray squares here. That's a total of 6. And each one of these, oh, wait. Okay, yeah, that basically did nothing. This one has 6. This one has 6. This one has 6. This one has 6. And this one also has 6. So that method did not work, but it was worth a shot. Another thing I noticed, which is really unique about this thing here, is that it guarantees that a corner, there has to be at least one corner that's shaded gray. And that corner that's shaded gray, the two stuff next to it has to be gray as well. So this sort of shape, I want to say, has to exist in whichever one we're looking at. So if we look as an example, right? If we look at answer choice A, the shape does actually exist. I'm gonna color the stuff in so it's a little more obvious, right? So that's sort of like 40, like 90-degree like angle thing, that like group of 3. It exists in A. B, it also exists. There's that corner, which is shaded. Yeah, there's that little thing. For answer choice C, it also exists. It's at the top left. Answer choice D, same thing. It's also at the top left. On the other hand, answer choice E. So this one is a little bit okay. There's a corner here. That one is shaded, but that one is not. So forget about this corner. This one is even worse. None of the ones that are supposed to be shaded are shaded. So basically what this tells us is that this thing does not exist in here, which means that it's impossible to get E by putting these two together. And that's our answer then. So answer check, correct.
All right, let's move on to the next problem. So we have Jane is playing basketball. In a series of 20 shots, Jane scored 55% of the time, and after 5 more shots, her scoring rate increased to 56%. On how many of the last 5 shots did she score? Okay, so to begin, in a problem like this, I kind of want to figure out what we already have. So if Jane scored 55% of the time, and there was 20 shots, that means that Jane scored 11 out of 20 of those shots, and she didn't score 9 out of the 20. So now, after 5 more shots, her scoring rate increased to 56%. So what is 5 more shots? 5 more shots would be 20 plus 5, or 25. And how many shots is 56%? Well, 56% is kind of a strange number where 55% and 20 were really nice. And then when we have 56%, it's not as nice to work with. But if we write it as a fraction, we see that 56 over 100 is a reducible fraction where both the numerator and the denominator are divisible by 4. So if we perform that simplification, we get that 56% is actually equal to 14 out of 25. And conveniently, we already have 25 shots when we add 5 more shots. So now the goal is that her scoring rate would increase to 14, where she scored 14 of the shots. And we already know that she scored 11 of the shots, so all we have to do is add 3 more and get C. And it looks like that's the consensus in chat, so hopefully we get that. We check our answer, we get C. All right.
Okay, here we go. Next question. Now we're in sort of like the final 10 range. So looks like we're doing pretty good on time. Okay, Michael has dogs, cows, cats, and kangaroos as pets. He tells Helen that he has 24 pets in total and that 1/8 of them are dogs, 3/4 of them are not cows, and 2/3 of them are not cats. How many kangaroos does Michael have? So this is a little bit strange, right? Like usually you just tell people how many cows or cats you have, but clearly Michael wanted to challenge Helen. So we're up for the challenge. So I'm tempted to pull out variables and be like, I don't know, D plus C plus C plus K equals 24 or something. But I'm not going to do that just yet. I'm going to try to harvest as much information as I can from the problem statement without having to do any algebra or anything yet. So, okay. First thing is 1/8 of them are dogs. So it's very easy. Dogs is 24 times 1/8. That is equal to 3. So 21 pets left. I'm gonna do this little tracking thing. 21 left. Okay. Um, okay, what else is there? 3/4 are not cows. So not cows, let's write that down. Not cows. 3/4, 24 times 3/4, which is equal to 18. Okay, not cats. 24 times 2/3, that's 16. And we actually want to find out how many kangaroos there are in the end. So, I think the easiest way to do this is to write a few basic variables. Like I don't want to get into any heavy algebra, but yeah, I don't see a way we can like easily see this without variables. So I'm gonna call okay, dogs we already know, so we're not gonna talk about that much. Let's label cows as let's call it W. Cats as okay, C, and then kangaroos as K. So, oh, I love how I just wrote K as K. But anyways, um, from the information we had earlier, we know that W plus C plus K, that's equal to 21, right? Because in total there's 24, but since we know 3 are dogs, it's 21. And we can also do something like not cows, right? So 3, which is the dogs, plus C plus K is equal to 18. And not cats is 3 plus the number of cows plus kangaroos, that's equal to 16. So what I'm going to do now is we basically just have to solve the equation and find K. The quickest way is we can just add these two together. That gets 6 plus C plus W plus 2K is equal to 34. And we can now subtract this one from this one. So this one minus this one, we get 6 plus K is equal to 13, which means K is equal to 7. Okay, does that look right? Yeah, looks like y'all agree with the answer choice D. Oh, actually, y'all have so many. Oh, wait a moment. I saw so many fractions and I was like, wait a moment. Did I do something not very smart? So, okay, yeah, I got tripped up a little bit. I did not need to use variables at all. So we did get the answer, but I want to talk about what you guys came up with, which is way faster than what I did. Basically, the thing here is right. 1/8 of them are dogs. We can just write that as 1/8 times 24, which is 3. Sorry, I wish I could just erase the stuff, but the 3/4 are not cows. That means 1/4 of them are cows, right? So 1/4 are cows. That means 1/4 times 24 is 6. 2/3 are not cats. That means 1/3 of them are cats, which means 1/3 times 24, that is 8. So add these three things up, that is 17. 24 minus 17, we get 7 kangaroos much faster. So yeah, that's awesome. That's why we love it when y'all share your ideas, because sometimes ours might be good, but not the best. All right, answer choice is D. Perfect.
All right. So now we're dealing with another problem that has algebra in it. So let's see what we can do. Julio has two cylindrical candles with different heights and diameters. The first candle lasts 6 hours, while the second candle lasts 8 hours. He lit both candles at the same time, and 3 hours later, both candles were at the same height. What was the ratio of their original heights? Okay. So there's a lot of variables going on with this problem. So let's see if we can try to break it down. So if the first candle lasts 6 hours, I'm just going to draw a candle. And the height and diameter, they're not drawn to proportion. So you can just disregard that. And then we have our 8 hours candle. And let's draw it with a little bit more height, like a smaller diameter. All right. So 3 hours later, both candles were the same height. So 3 hours later, that means that the 6-hour candle is going to amount to half of what it usually was. So let's call the 6-hour candle have a height of A. The height is equal to, actually, let's let the height of the 6-hour candle be H1 and the diameter be D1. And similarly, the 8-hour candle, let's let it have a height of H2 and a diameter of D2. So 3 hours later, the heights are both the same. So let's consider each example individually. So 3 hours for a 6-hour candle means the height would be reduced to half. There's no like shrinking of the diameter. So if you envision a candle, it's going to be melting down vertically. It's not going to be shrinking horizontally. It's just going to be a vertical decrease. So that means we're going to have H1 over 2 as the height after 3 hours. But in the 3-hour case for the 8-hour candle, we're not going to have a full half of the height decrease. Instead, it's only going to be 3/8 of the height that's decreased. So after that, we're going to have 5H1 over 8. So now that we have each of those numbers finalized, we can have them equal each other since they're both the same height. And that means that 8H1 is equal to 10. Oh, sorry, this should say 5H2. So 8H1 is equal to 10H2. And if we combine those and do some simplification, we get that what was the ratio of the original heads? Well, it would be H1 to H2, which is 5:4. And I actually think this problem is really interesting because it shows how even though we set up the variables for diameter in both of these scenarios, they're actually irrelevant in this case. And I was thinking that the diameters would be helpful if we consider something like the volumes of the candles, but since the problem never actually asks about the volumes, we don't even need to consider that. And the answer is C, yes, as you guys are saying in the chat. And I've noticed a lot of C's in this question, so that's interesting. Yes, and we get C, as we found in the problem.
All right. Okay. I think this is down to our final five now. So we might need to take a little bit extra time, but we'll see. 25 minutes, we have three more. So the integers from 1 to n, inclusive, are equally spaced in order around a circle. So what happens is we're doing it's like a clock. So if n was 12, this would be a clock. The diameter through the position of the integer 7 also goes through the position of 23, as shown. And we want to know the value of n, which is in this case, if it goes to 23, what is the total number of numbers, or the highest number in this circle? Okay, so actually I immediately know how to solve this, but let's hear. What do you guys think? What type of ideas should we try here? So, oh, we have 30 questions. Okay, that's good. That's a long time. Okay. If 7 is 1, then 23 is 16. Oh, that's a great idea. I think 23 might actually become 17. So what was suggested here is that one thing we could try to think about is what if we just sort of shifted everything back, right? That's a bad circle. But if we shifted 7 back to 1, right? -6, 7, -6, we shifted 6 spots and back to 1. 23 also gets shifted 6 spots, and it becomes 23 minus 6, which is 17. So in this way, we know if we start at 1, the opposite of it is 17. So yeah, and then someone is saying multiply by 2. Okay, yeah, we have a few suggestions of 17 multiplied by 2. And the reason behind that is because uh I mean it's halfway through, right? So it would be very logical to multiply 17 by 2 to get an answer. But let's try to think about why exactly, right? Because the difficulty of this problem doesn't lie in the fact that we multiply by 2. It's quite obvious that we have to find some way to multiply by 2 because we're dealing with half circles. Actually, the way I would think about this is going from 1 to 17. That's a plus 16, right? That's a plus 16 movement. Going from 17 to 1, that's another plus 16 movement. So actually, I think this is less about 17. I think this is actually more about 16. Because what matters isn't are we starting at 1 or 17, right? Are we starting at 7 or 23? What matters is how far are we traveling to get to it, right? And every time you hit a new number, let's say, right? 1, 2, 3, 4, 5, you go hit 16 new numbers, you get 17, you hit 16 new numbers, you arrive back at 1. So that makes this 16 multiplied by 2, which is equal to 32, I believe. Yeah, does that make sense? All right. Someone says 16 minus 1 equals 15. Okay, wait. Before we reveal the answer to this, I actually have another method I want to test. Um, Wait, actually, never mind. It's the same method. When I first saw this problem, I was gonna be like, okay, what's 23 minus 7, right? That's 16. And then 16 multiplied by 2, that's 32. So it's the same method. I think it should be B, 16. And B, 32, 16 times 2. And that is correct. Awesome.
All right. That was a really fun problem. Let's see what we have next. Ooh, okay. So Natasha has many sticks of length 1. The sticks are colored either blue, red, yellow, or green. She wants to make a 3 by 3 grid as shown so that each 1 by 1 square in the grid has 4 sides of different colors. And what is the smallest number of green sticks that she could use? Okay. So let's see what we can do here. So I want to see how we can color this in the most effective way so that we're not using any green. Well, in the very first square, let's start in this upper left corner. Okay, so one of the sticks needs to be green because we only have 4 colors and all 4 of the sides need to be different colors. So the question comes in, which side should we make green? Well, if we make this corner side green, which I've circled, then if we move on to the next square here, we need to color another stick green. So let's not do that. Let's have it in a different place. Essentially, the goal of this is that we want to make sure that the green or the stick is in as many squares as possible. So let's see what we can do. If we have the green as not the top left, but actually one of the middle 2 sides, so either the bottom or the rightmost side, we could have it in more squares, which will be more helpful. Yeah, it's basically what the comment said. Don't put green on edge. Ooh, I see a note that says 9 divided by 2 is equal to 4.5, rounds up to 5, so C. That's a really interesting thing. And I see where you got that intuition from. Because in every square, we want to make sure that the green is touching something else. So, for example, let's say we want this to be green. Then we don't need a green over here. And then we also don't need a green but we need a green on the final square on the top right. But let's not make it like this, because then we have that top middle square with 2 greens. So instead, let's consider another arrangement. And here's the bigger version of the square. So let's see if we can color this in a way that's the best. And although I feel like in the beginning, this doesn't seem like the most efficient strategy to do this, I think it's really helpful when it comes to understanding why we put the green where they are. So let's put the green here to start. And then we can't put the green here because that'll be 2 greens in 1 square. And we can't put it on this edge or this edge because that will not be efficient overall. Yeah, so what if we put the green here? Okay, and I'll put X's in the squares that are covered. So this square is covered, this square is covered, this square is covered, and this square is covered. So moving on to the bottom square. If we see that this is already covered and we can't put another green here because that would violate this middle square, and we can't put the greens here or here. So that means we have to put a green here. And once again, we can put X here and an X here. Now we have these 3 squares left. And if we're looking at the answer choices, we know that it's either 3, 4, 5, 6, or 7. And we already used 3, so let's try to minimize as much as possible coming from here. So looking at this square, we can perform a very similar process from what we've done before. We can't put a green stick here, we can't put it here, and we can't put it here. So the only possible one that is left is right here, and this square is covered. But now we have a dilemma, which is what are we going to do with this middle square? If we put a green here, we're going to have 4 sides that are the same. If we put it here, it's going to be this square, here's going to be this square, and here's going to be this square. So what are we going to do now? There seems to be having an issue with the way we set this up originally. And when we run into this problem like this, we need to figure out what can we do to solve this problem. Well, one of the ways that you might consider is that to put one on the edge. Exactly. So instead of putting one here, let's see. Instead of making this edge green, we want to draw in, okay, pretend this is a white edge and I didn't color it out, but let's put one here and then one here. And now we have an X here. So let's just recap and make sure that we haven't violated anything by making this change. This top one has one green, this one has this green, this one has this green, this one has that green, this one has this green, this one has this green, and this here has this green, this one has this green, and this one has this green. So if we add it all up, it's 1, 2, 3, 4, 5. Yeah, so try to not use green sticks and put the red, blue, and yellow first. And then we can place the green. So noticing by how we changed this arrangement in the slightest made it satisfy the middle square. And I guess we got lucky in this problem because we don't want to do all this arrangement and then realize that there's one piece that's wrong and we have to start from the beginning. So I'm happy that we could only change one thing and we got 5. But let's just make sure this is right. Yes, we got C or 5. Ooh, okay, before we go on, someone says, I have an idea. Put 3 greens on the second column, 1 green in the bottom of the third column, and a green on the rightmost of the second row. Ooh, okay, let's go back and see if this works. And by the way, notice that this is not the only arrangement that could work. Like, there's gonna be much more options that could work. And to look at this, let's use blue instead of green, but it's the same concept. So put 3 in the second column. Okay, so 3 in the second column, I think that would go something like blue, blue, blue. So that would get this second column would be good. And then 1, it still adds up to 5, so we're good. Yes, so even if this would work, it would still add up to 5, which means that it should work in the end. But I think that 3 in the second column, unless I'm misinterpreting your result, would have some overlap. So maybe we could put some in the second column vertical and it should align. And notice that we can still like rotate the square. And if we're rotating it, it wouldn't change the coloring problems. 3 greens on the second column. Oh, I think they mean row. Oh, okay, I see. Vertical second column. Okay. Yeah, that would work too, I think. Okay, cool. Nice alternate solution.
Okay, next question. That'll be 25. So now we have like 3 more. Okay. Elizabeth is Elizabeta had a large bag of 60 chocolates. She started by eating 1/10 of them on Monday. Okay, I'm actually gonna write these as numbers because I'm not very good at reading the text. 1/9 of the remainder. Okay, remainder is an important word. 1/9, 1/8, and then 1/7 on Thursday, and so on until she eats half the chocolates remaining from the previous day. So she goes all the way until 1/2. How many chocolates does she have left? So I'm gonna assume, yeah. So you start with 60 chocolates, you eat 1/10 of them, then you eat 1/9 of the remainder, then you eat 1/8 of the remainder, then you eat 1/7 of the remainder, blah blah blah, and then you eat 1/2 of the remainder. So the first thing I'm gonna do is I'm just gonna like test out the first few like 1/10s, 1/9s to see if we can find some sort of pattern. And then I'll draw like a chocolate progression chart. So for 60, if you eat 1/10 of them, then you eat 6. Um, if you eat 6, you have 54 left. Okay, day 1 passed. Day 2 on Tuesday, 1/9 of the remainder. So 1/9 of 54, that's 6. So we eat 6. 54 minus 6, we're gonna have 48 left. Okay, 1/8 1/8 of the remainder, that's 6. If we eat 6, we're gonna have 42 left. So I think we're starting to see some sort of pattern here, right? As someone said, isn't it just 6? Indeed, yes, it is just 6. Because every time we subtract 6, we're sort of just taking away like a piece. And then that's why the denominator goes down by 1, because a value of 6 is gone. So the denominator goes down by 1, yet we still get 6, right? It's just 6, 6, 6, 6, 6 a lot of times. And now the way we can do it is we engage in the act of eating 6 9 times. And how do we know that? It's because 10, 9, 8, 7, 6, 5, 2, 6, 5, 4, 3, 2, that's 9 total numbers, right? So 10 minus 1, that's 9 total numbers. So we do the action of eat 6 9 times, which means we should get 60 minus 9 times 6, which is equal to 6, and that's answer choice E. Yeah, so I was wondering why they didn't do 1, 2, 3, 4, 5, because the answer is 6 and we can't do 1, 2, 3, 4, 5. So indeed, the answer is E. Perfect.
Okay. Ooh, that was a fun problem. So now we're working with some more ratios, which we just discussed. So the question reads, when Ria and Flora compared their savings, they found that the ratio of their savings was 5 to 3. Then Ria bought a tablet for $160, and the ratio of their savings changed to 3 to 5. How many dollars did Ria have before buying the tablet? Well, there's a couple different ways to do this problem. The first way that immediately comes to mind is actually plugging in the answer choices and then using them. But I want to find a cleaner solution. So let's say the total amount of savings was 5x to 3x in the beginning, and which means that if you add these two values, their initial savings was 8x, and Ria had 5x of those dollars. So now their savings after the tablet purchase is 8x minus 160. And this is actually 3 to 5. So if we have a 3 to 5 ratio and the whole is this, we say that 3 parts of this, or 3/8 of the total, would go to Ria, and then 5/8 would go to Flora. So if let's just consider Flora's part, because we know that Flora did not do anything to her share. So she actually has the same dollar amount of dollars before and after, even though her share seemingly increased. So if we have 5/8 of this value, we get that this is 5x minus 160 times 5/8. 160 divided by 8 is 20. 20 times 5 is 100. So 5x minus 100 is equal to 3x. So now all we have to do is solve that equation. 3x is equal to 5x minus 100, or minus 2x is equal to minus 100, and x is equal to 50. So simply we can plug this back in. 5 as x is equal to 5 times 50, and that is 250. But remember what I said initially, where we can plug our answer choices back in and see if it works. So let's do exactly that. Initially, if Ria had 250, then Flora would have 50 times 3, or 150. And now if we have that, and she uses her money, and now it's 90, it would go to 90 to 150. And if you simplify this ratio, you would get 3 over 5, so our answer is indeed right. Oh, and it looks like the answer is C again. I think we need to start counting how many C's there were in this set.
All right. So that brings us to our last question. Another geometry. So let's take a look at this. So my first impression is actually I'm a little bit scared because there's this random intersection that might be a little bit hard to deal with. But that's all right. The diagram shows the square ABCD with P, Q, and R as midpoints of sides DA, BC, and CD respectively. What fraction of the square ABCD is shaded? So, okay, I feel like I start all my discussions with so, but the first thing I notice about this is that this shaded area is a little bit irregular. And as one person said in the chat, we might want to consider doing like the whole thing minus the non-shaded areas. That way we can, get this sort of complicated figure because we have two right triangles that are non-shaded and then one isosceles triangle. So I agree with that. And what I'm going to do now first, though, to just make our lives a little bit easier, is that this question never gives us any side lengths. And in the end, it's just asking us for a ratio, like the fraction. So in order to make our lives easier, I'm going to label the side length of the square as 4. And that's the only thing I'm going to label. The side length will be 4. And then we'll find the fraction, because the total area of ABCD, that's 4 squared, which is equal to 16. So now there's a few easy things, right? If we know the side lengths are 4, we know R is the midpoint, so these are 2 and 4. So we basically have two right triangles, 2 multiplied by half times base, 2 times the height, which is 4. So half times 2 times 4, that's 4 multiplied by 2, that's equal to 8. Now, the slightly more challenging part is to find what is the area of this triangle right here. We know the half, we know the base, but what is the height? That's the difficult part. What ideas do y'all have? So, oh yeah, someone did mention give random side lengths. That's great. So someone also talked about, okay, I'm not too sure, right? We just need to find the height. So what's one thing? The first thing I'm gonna do is that we can draw the height. That's the height, right? And there's another important thing is that this is an isosceles triangle, which means that the base of the height is exactly the midpoint of AB. So that's the midpoint. Another piece of information that we haven't used is that P and Q, I know I kind of cover them with the fours, but P and Q are midpoints as well. Someone once told me when they were teaching me geometry, it's like, for a lot of geometry problems, it just comes down to like, when you're stuck, think about what information you haven't used, because there's usually a reason they give you that information. Very rarely in math contests do they give you like extra information that you don't need. Sometimes they do that to troll you a little bit, but in this problem, I'm going to assume P and Q being midpoints are quite important, because if we drag P and Q up and down, and if they're like not midpoints, then that's actually going to change the area. So them being midpoints is important. It looks like okay, we have people saying the height is 1, and we also have someone saying it looks like the midpoint of the line. So I'm not entirely sure what you mean by the line, but the height. Okay, yeah, height is quite important. What do we think, right? How does this height relate to like the rest of the numbers? Okay, so I think, okay, because of the half, um, 1.8 of the entire area. Okay, 1/8 of the entire area. Oh, I see what you guys mean. Okay. Yeah, the midpoints I labeled, this is the midpoint. I just drew like a big yellow circle there. I can draw a white yellow circle at the midpoints as well. That way we can visually see which ones are the midpoints. So this is also midpoint, right? And R is also midpoint. So those are the midpoints. Um, just break the square into sections. That's actually a great idea. That's a great idea. I'll talk about that in a moment. I'll talk about that in just a moment. So, um, the thing about the heights that I want to talk about is, let's zoom in. Okay, I don't know how to zoom in on this whiteboard actually, but this, the important thing is to look at, I'm gonna try to find a color where I can draw this triangle. The important thing is to look at this right triangle compared to this height. So the professional way to say this is that this triangle is similar to this triangle because we can easily see that all of the angles are equal, right? It's sort of like a projection of the triangle out. And because this point here is the midpoint, we can also, this means that this side here is 1/2 the length of the side AB. The same logic applies to the height here. This height is 1/2 the height of this height right here. And since we know this height right here is 2, that means this height right here must be 1/2 of 2, which is 1. So that means the height of this triangle is actually 1. So 1/2 times 4 times 1, that makes the area 2. So now we just have to find the fraction, right? 2 plus 8 over 16, that's equal to 5 over 8, which is answer choice B. Awesome. Okay. So that's the way to solve it using like our formulas, but someone else did mention that one thing we could do is we can just split this up into sections that are convenient to us. So I see we're a little over time, but I just want to do this really quick because I think that's a great idea. If we want to find the area of this thing, right, we can split it into half first, right? So this section is now a half. And then we can break it down even further. I'm trying to draw these lines as perfect as possible. There we go. So in case you can't see, I'll also draw the diagonals. Yeah. So now it's very clear that each of these little areas are equal to each other, right? And since there's a total of 8 pieces and 2 pieces here, that's 2 out of 8. But since we're only half of the square, that triangle right there will actually be 1/8 of the entire area. And of course, we can use this and solve the problem as well. But great job. Those are some lovely ideas. Okay. Wait, did I make a mistake? Okay. 8 plus 2. Wait, yeah. Okay, I did make a mistake. I forgot the last thing. So, the black stuff is 5 over 8. That's correct. But we actually wanted the shaded stuff, which ironically is like the slightly grayer part. So the answer isn't 5/8. That was a great catch by. There we go. The answer is 3/8, not 5/8. But yeah, great job, everyone. I really liked hearing all of your ideas. And this was a challenging problem, but we got there in the end. Awesome. Okay, so that'll bring us to the end of our Math Kangaroo session. Hope you enjoyed it. And Sneha, do you have anything else?
I guess thank you all for your amazing participation. It was a lot of fun hosting this, and I hope you had a lot of fun watching too.
Yeah, awesome. So in that case, we're done for today. Thanks for coming and hope to see you all next time. Bye-bye.
Yeah. Bye-bye.
All right, let's see. I think we have to close the bridge. Bye, everyone.
Bye, everyone. Nice to have you.
All right, in that case, I will leave. Bye-bye.
Bye, Dean. See you later.